Hi everyone, thanks for coming to this session. In this track we had 3 lectures about IE and now some refreshments performance-wise. Next lecture is about architectural patterns for caching microservices, and I am happy to introduce Rafal Leszko. Rafal, you have the stage.
Thank you. So I'm Rafał. I came from Poland, and I will tell you about caching, and especially about architectural patterns that you can use in your microservice system. But first, a few words about myself. So I'm a cloud software engineer at Hazelcast. I used to work at Google and CERN before. I'm also an author of the book Continuous Delivery with Docker and Jenkins. And from time to time, I do conference speaking and trainings as a side activity. Also, a few words about Hazelcast. So Hazelcast is a distributed company with around 140 employees in total, about 40 engineers. We are distributed in 2 meanings. One meaning is we produce distributed software, but the second meaning is that we all work remotely. So we have people all over the world, which is kind of nice. We have 2 guys in Zagreb, so when I came here, I could work with them. We have 3 products. First, the most known is Hazelcast IMDG, memory data grid, which is kind of caching solution or key value data store kept in memory. The second product is Hazelcast Jet, which is a library for stream processing. And the third one is brand new, is Hazelcast Cloud, which is Hazelcast put into cloud, so you don't have to run your own cache server, but use the solution from the cloud. Our agenda for today is super simple. So there will be a very short introduction about caching in general, and then we will walk through all architectural patterns that you can use in your system. I would like you to think about 2 things. If you happen to work at the microservice system, think about which of the pattern you use. You must use one of them because this list is complete. And the second thing I would like you to ask yourself is, would it make sense to move to any other patterns for the reasons we will mention? About caching, so everybody does caching. Caching is everywhere. Like we do it mainly for 2 reasons. One is the most obvious, for the performance. So we don't want to do some long-lasting calculation. So we cache the value and then return the cached value instead. Second thing is about resilience. So you can think that your system may be down, or part of your system, but if you return the cached value, user may not realize even. It depends on your use case, but as a good example, think about Amazon recommendations. You can still give some recommendation even if your recommendation service is down, because it doesn't matter. I mean, it matters, but it's not the most important to give the accurate answer. But how to do it in microservices? So this is a sample microservice architecture. We have a lot of services, they use each other, they can be written, they have different versions, they can be written in different programming languages. And the question is, where is the right place to cache? Should it be inside of this service, or as a separate cache server, or in front of each service? And that is what this talk is about. So let's go to the point. The first architectural pattern is the simplest one possible. It's embedded cache. It looks as follows. A request comes to our system, it goes to the load balancer. Load balancer forwards the request to one of application web services. Then the application service checks in a cache which it calls internally, checks if the request is already executed. If yes, return the cached value. If no, do some long-lasting business logic and put it into cache and return the response. This long-lasting business logic, it can be anything that is time-consuming, call to the database, or call to external service, or call to some internal service, or just a long-lasting computation. This is very simple. We can even think about implementing this ourselves. Like, if you like Java, then that would be the algorithm. Exactly what we described. Request, we check the request if it is in the cache. If yes, return the cache value. If not, do processing, put it into cache, and return the response. You could do it, but don't do it. Because concurrent hash map or any Java collection is not a cache. It has no eviction policies, no max size limit, no statistics, no built-in cache loaders, no expiration time, no notification mechanism, and it's just not a good thing to use it. If you want to use a simple embedded cache, then use a library like Guava in Java. This is very good because all these parameters which are missing in concurrent hash map, you can define them while building your cache. Another solution is cache. We can even move this caching layer one abstraction level higher and put the cache into the application layer, into the framework we use. Like everybody uses Spring with Java. So if you happen to use Spring, you just use one keyword cacheable, and then all calls to this method will be cached. Meaning that this find book in slow source will be called only if the ISBN was not executed, if this method was not yet executed with the given ISBN. But be careful because Spring uses concurrent hash map by default, so you're better off defining your own cache manager. Coming back to our diagram, so this is very simple and this is good for a lot of cases. However, it has one problem. Imagine that a request comes to our system and then the first request goes to the application on the top. It is cached, everything fine, but the next request goes to the application on the bottom. Then we have to do the processing again because the caches are completely separated. So one improvement to this pattern would be embedded distributed cache. It's still the same pattern in terms of architecture. However, this time both caches will form one cluster, like here. So you can use Hazelcast for that. Hazelcast is just a library which will form one distributed cache cluster from your embedded caches in your applications. It is just a library, so we can use it together with the Spring. So, just by defining cache manager, every time you use cacheable in your Spring application, it will use this distributed cache. You may wonder how do this distributed cache, how do they form cluster together? So our approach is to provide for each environment a plugin so that the caches will, in each application, they will discover themselves automatically to form one distributed cache cluster. So we have, for most cloud providers, we have a plugin. If you use something more specific, you can always set up your own Eureka service registry and then use it as a service registry for Hazelcast. So that's about embedded cache and embedded distributed cache. A short summary. So pros and cons. Good thing is that the configuration is super simple. It goes together with your application. You have very low latency because it's the same JVM, or if you don't use Java, it's the same process. So you cannot do anything better. And you don't need any separate ops team or DevOps effort to maintain the caching because it goes together with your application. From the downsides, the management is not flexible because if you want to scale up your cache, you need to do it together with your application. So if you have a lot of data, suddenly you need bigger cache, then the only way is to scale up your application. It's limited to the JVM-based application or your programming language of choice. And the data is co-located with the applications. which may not sound like a big thing, but actually for big enterprises it is usually a problem that the data is stored together with your application service. We covered embedded cache, distributed cache. The next one is client server. Client server is kind of database style. So we have the flow is the same. I mean, the request goes to load balancer, it goes to one of the services. Then the application web service uses a cache client to connect to one cache server, which is deployed somewhere. If we compare this to the embedded cache, there are two main differences. One is obvious, it is this part. So we have a new thing in our architecture, in our infrastructure, which requires separate DevOps effort, or you need to maintain this thing. It has good size and bad size. I mean, it requires effort, but on the other hand, you can scale it up, down as you want, not touching your application. But the second thing that is different comparing to the embedded cache is actually this part. So now the application uses a cache client which connects to the cache server. Cache client and cache server, they have a well-defined protocol. That means that your application can be written in any programming language because you can use the cache client from a different programming language. And that is very useful, especially in the microservices, where that's a very common approach that you have one cache server and a lot of microservices written in different programming languages, and they can all connect to this server. In this pattern, you can also use other solutions than Hazelcast, like the most popular is Redis, obviously. If you work in some legacy project, or then you may also find Memcached. So this Redis and Memcached, you cannot even use them embedded because they are written, I guess, in C. So you cannot embed them in your Java or whatever application. So coming back to our diagram, so this server has to be managed like separately by usually it's by big organizations, even a separate team. We can even think about moving this outside our organization and move it into the cloud. Cloud is still like kind of client server, but difference is that cache is no longer in our infrastructure, but it is located in some cloud provider infrastructure. But in terms of this diagram, it is the same. We still use a client to connect to some cache server. Difference is that we don't need to do any management. But obviously we have to pay the cloud provider to do it for us. So, how would it look like in our Spring configuration? I will show you the example for Hazelcast. As I told you, Hazelcast Cloud is a new product from us. So, but you can already use it. It's already on working. You can create clusters for free. Redis has their own solutions, so they have Redis Labs, the same thing. The Hazelcast configuration of the cache manager or this cache client looks like this. So there is actually nothing super fancy here. You just provide. You don't provide any URL. You provide some discovery token, so how to find your cluster, and then the password, the name of the cluster, and the password. And with this configuration, the client can connect to the server that is in the cloud. Short summary. What is good and bad of the client server and cloud cache solution? So the good things, data is finally separated from the applications, which is, as I told you, most enterprises, they wanted. Separate management. Suddenly you have a peak load, you can scale up your cache cluster without touching your application. It's programming language agnostic because you can use any cache client written in any programming language, or if there is no such thing, you use some niche programming language, you can always write your own because the protocol is well defined. From the downsides, we require separate ops effort and higher latency. So we didn't speak about latency, but embedded was simple. Latency was super low. It was the same JVM, no problem. Here we have to think about latency. If we set up our own server, it must be in the same local network. If we set up it in the cloud, then what we do in Hazelcast is when you create, there's a web console and you create your cluster, you specify which region should it be in, but also specify which cloud provider, so underlying cloud provider, like we use underneath either AWS, GCP or Azure for now. So you have to define which one, and then you do the VPC peering so that it is really in the same, your application and your cache is really in the same virtual network. Because one thing that is very important is caching. In caching, we are in the domain of in-memory data processing, in the memory data storage, which has, this domain has much more strict requirements than databases in terms of latency. You expect it into, even like one network hop is a lot. So we try to be really in the same network. We cover like the first two architectural patterns, like embedded and client server. There were kind of old. You might have guessed it yourself because it's like they are old in this world. This sidecar is something completely new. Sidecar is limited to containers and containerized environments. This diagram is limited to Kubernetes. So a few words about Kubernetes. So in Kubernetes, a deployment unit in Kubernetes is a pod. And a pod can have one or many containers. Usually a pod has one container, and this container is your web service application. However, in some cases you can have additional containers for some additional functionalities. For example, it can be a logging agent that will send your logs to some logging system. And this additional container is called a sidecar container. So you deploy two containers in one pod, and one pod, everything you deploy in one pod, it is always deployed on the same physical machine. That is very important. Coming back to this diagram. So again, the request comes to our system. It goes to the Kubernetes service, which is kind of a load balancer in the Kubernetes world. Then it goes to one of the pods. In this pod, it goes to the application container. Then the application container uses cache client to connect to cache server, but this cache server is located on the same pod, so it's located on the local host always. And all these cache sidecars, they all form one cache cluster. So this solution is somewhere in between embedded and client server. It is similar to embedded because the cache is an application that are deployed on the same physical machine. They use the same resource pool. They scale up and down together. However, it's always also similar to client server because you can use different programming languages, and because after all it uses cache client to connect to the cache server. Spring configuration for this, it uses like a static configuration, so it's always on the local host, but after all it's dynamic because this container are always deployed together. Pros and cons, like configuration is simple again, it's programming language agnostic, we again have low latency, there is some kind of isolation between data and applications. From the downside, it's limited to container-based environments, mainly Kubernetes. The management is not flexible, and data is co-located on the same application pod, which can be a problem or not, depending on your use case. X1 is something completely different, because so far all these patterns, in all these patterns, application was aware of the cache. Now we'll do something different in reverse proxy. So application will not even know that cache exists. We'll put the cache in front of the application. So in this diagram, request goes to our system, it goes to the load balancer, and the cache is located before or just after the load balancer. And only if the cache value is not found in the cache, it goes to one of the web services. You can use it with Nginx. This is a very major solution. Everybody uses Nginx for reverse proxy. So you can just add a configuration to Nginx to cache your requests. And it is very, very simple. Nginx has some problems, like it's only for HTTP, the cache is not distributed, it's not highly available, and data is stored on the disk. We can think about this philosophy of application not knowing about cache, combine it together with Sidecar, and like this to see the last caching pattern, which is called reverse proxy Sidecar. Again, as with Sidecar, we will limit ourselves to Kubernetes. This time request goes to the Kubernetes server, is load balanced to one of the pods. But in the pod, it's not the application that receives the request, but a reverse proxy cache container. And then this reverse proxy cache container decides if I already have the cached value, return the cached value. If no, go to the application, and application processes the request and goes back to this reverse proxy container. So this fact that application does not even know about the existence of the cache has some good and bad sides, as you can imagine. Starting from the good sides. So let's come back to the diagram we've seen like just at the beginning. So we have a classic microservice architecture, services in different versions, different programming languages, they use each other, and so on. Now you see such an architecture, and without modifying any code of the service, you can say, I would like to have cache in this and this services. So you define cache in a declarative manner, which is, if you think about it, it's super cool, because you don't even have to, you don't even have to change the code or build again any of the services. It also, if you are really into the Kubernetes and containers, it goes with the philosophy of service mesh and Istio, where you define a declarative manner like traffic and everything. You could define the caching. Istio does not have caching yet, but they implementing this. So probably next year, I think you will be able to use this pattern with Istio. But such approach that application is not aware of the cache also had some bad sides. If you detach the caching from the application, there is one thing that becomes way more difficult. And that one thing is cache invalidation. So if you look anywhere on the internet, what causes most issues with caching, everyone will tell you the same, it's cache invalidation. Meaning, when to decide that the cached value is not valid anymore, that it's stale, that I should not use the cached value but go directly to the database or to call some external service. If application is aware of the cache, we can have some business logic for this. Like in Spring, say, okay, if this or this happens, then don't use cache. Remove the value from the cache. However, if the application is not aware of the cache, all we can do is some standard HTTP things like timeouts, ETAG, everything you normally have in the browser. So it's like, it's kind of limited. It actually limits to timeouts, which may be good enough or may not be good enough for your case. Because if you need really high consistency, then obviously it's not good enough. If not, then this pattern is actually very good. Quick summary, like, good thing is that it's configuration based, no need to change any application. It's programming language agnostic, it's actually everything agnostic because it does not even touch your code. It's very consistent with the containers world, with the service mesh, Istio. That's the way world is going right now. From the downside, like as we said, invalidation is difficult. Also, there is no mature solution at the moment. We in Hazelcast did a proof of concept, which you can play with, but not necessarily use it on any production. Istio, as I told you, they are working on that, so it will come, but as of now, there is no major solution for reverse proxy sidecar. For reverse proxy itself, you can use Nginx. And it is protocol based, which is not such a big deal after all, because in the current world everybody uses HTTP, and that's a standard. So with this, like, we covered all the patterns. So as a quick summary, I know there are a lot of these patterns, so instead of repeating myself again, I will just do a quick decision tree, which may help you decide which of the patterns is a valid one. So the first question I would ask: does my application need to be aware of the cache? If no, then is my environment container based? If no, use reverse proxy with Nginx. If yes, use reverse proxy sidecar as soon as there is a mature solution available. If my application needs to be aware of caching, then the next question is, do I have a lot of data or some security restrictions? If no, then should my caching solution be language agnostic, or do I run in a container environment? If no, use embedded cache. If yes, use sidecar. If you happen to have a lot of data, work in a big organization, then the last question is my deployment environment a cloud? If no, client server on premise. If yes, then the cloud solution. That is obviously a little simplified, because sometimes it requires more analysis, but this is a good starting point if you start a new architecture for your system. As the last slide, I proposed a few resources. So the first one is Hazelcast sidecar container pattern. It's a blog post how to use Hazelcast as a sidecar. Second one is this reverse proxy sidecar prototype proof of concept that you can play with, but not necessarily use it on production at the moment. Two other links are the cache best practices is a blog post. It's a very good blog post about caching in general. And the last one is how to use, it's a video, very good video about how to use Nginx as a reverse proxy caching. And with this last slide, I would like to thank you. It was really a pleasure to be here. If you have some question, then I will be around. Thank you.